6.1, rational functions. So a rational function written f of x equals some p of x divided by q of x. This is where p and q are polynomials with q of x not equal to 0. Why can't it be equal to 0? Can't divide by 0. Dividing by 0 is an undefined operation. So f is undefined for q of x equal to 0. Okay? So the domain of f, is all real numbers x such that q of x is not equal to 0. So how do I find the domain? It's all real numbers except x values where the denominator is equal to 0. So we're looking to avoid situations where the denominator equals 0. Okay? So let's work through some problems together. Find the domain of a rational function. Find the domain of a rational function. So my first one is f of x equals x squared minus 9 over x minus 3. Okay? So how do I find the domain? Sometimes it's going through and figuring out where all the x's at work. That's one way to do it, but that takes a long time. So sometimes it's better to figure out all the ones that don't work and then avoid those situations. So where does it not work? It doesn't work when the denominator equal to 0. So set the denominator equal to 0. X minus 3 equal to 0. Solve for x. So add 3 to both sides. So x equal to 3 is bad. So we do not want this value. So if I'm looking on a number line, I want everything except 3. So everything from negative infinity up to 3, and then from 3 out to positive infinity. So what does that look like? The domain is equal to what? Negative infinity to 3, union, parentheses, 3 to infinity. We skip over our 3 there, okay? That's the one value that we're not going to use. All right, let's try another one. B. G of x equals x over x squared minus 9. X squared minus 9. All right, same thing. To figure out the domain, we need to look and say, okay, what values can I not have? Well, I can't have the denominator equal to 0, so I have x squared minus 9 equal to 0. Two ways to do this. Either you can add 9 to both sides and get x squared equals 9, and then to get rid of x squared, I square root, and when I square root, I have a plus and a minus. Square root of 9 is 3, so that's plus or minus 3. Those are my bad values. Or the other way is to see that this factors to x minus 3, x plus 3 equal to 0. And so this gets me x minus 3 equals 0, or x plus 3 equal to 0. So x equals 3, or x equals negative 3. And so both of them get me the same solution. Okay? So either way you want to do it, I don't care. Just solve for x. Figure out what x can't be. Now, if I look at a number line, right, I can't have -3 and I can't have 3, but everything else works. So how does this look? In interval notation, we go from -infinity, read from left to right, okay? -infinity to -3, union, skip over -3 and go up to 3. Okay, we got this one, now we got that one. Now we just have the last one to do, union 3 to infinity. And that, my friends, is the domain of that g function, okay? All right, one more, just to make sure we got this. C, let's do some h of x equals x plus 3 over x squared plus 9. Okay, so once again, set the denominator equal to 0. X squared plus 9 equal to 0. Minus 9 minus 9. So that tells me x squared equals -9. Square root both sides, but we have an issue. When I take the square root of a negative number, that's no longer real. This is imaginary. This gets me plus or minus 3i. Okay, so x is equal to plus or minus 3i. This is not real. So there are no real x values where the denominator is equal to 0. And if you think about it, this x squared term, anytime I plug a number into x squared, it's going to become positive. So the smallest thing that this positive thing could be is 0. But if I take that number and add 9 to it, then it can never equal to 0. So this whole h of x, I can never divide by 0. So that means every value of x that's real works. So the domain here is -infinity to positive infinity. So it's all real numbers. Or you could put R, okay? You know, whatever you want to do. Okay, so the question you might have is, what happens at these, quote, bad values? Okay? What happens at these bad values? So vertical asymptotes. Vertical asymptote. A vertical line x equal to c where f of x, a function f of x, increases or decreases without bound as x gets really close to c. Okay, so what does this mean? What does this mean here? All right. So vertical asymptotes, maybe you've seen those dashed lines, like maybe x equals -2. Vertical asymptote, my function, as we get closer and closer to this value, it's increasing, increasing, increasing up to infinity, right? It's increasing without bound. But you could also have it as it gets close to -2. You could also have it be going down, 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 decreasing without bound. Okay, so that's why I had that increasing or decreasing. So it could be going down to -infinity like that. All right, so here's the deal. Rational functions don't cross vertical asymptotes. Okay, they do not cross these vertical asymptotes. All right, they don't cross them. So we get really close to x equal -2, but we never cross it. All right, there's no connection between this side of the graph and the other side of the graph, okay? They don't magically connect down the middle. They're split, they're divided by that vertical asymptote, okay? All right. Let's talk about how to find a vertical asymptote, okay? A vertical asymptote. So g of x equals x over x squared minus 9. All right, so a problem that we did earlier. How do we find vertical asymptotes? Well, vertical asymptotes occur when it looks like we're about to try to divide by 0. So what do I do first? Step 1, so for finding vertical asymptotes, I'm going to say VA for vertical asymptotes. So how do I do it? Number 1, factor. Okay? Number 2, simplify. Number 3, set denominator equal to 0. Okay, set denominator equal to 0. All right, so first off, factor. So when I factor this, the top is just x, the numerator is x, the denominator, this factors, it's a difference of squares. So it's x minus 3, square root of 9 is 3, and then x plus 3, that's your difference of squares. Now simplify. Is there anything in common between the numerator and the denominator? No, a factor of x doesn't cancel with x minus 3 factor or x plus 3 factor. So what do I do now? I set the denominator equal to 0, okay, and solve for x. See what my, quote, bad values are. So x minus 3 equals 0, or x plus 3 equal to 0. So that means x equals 3 or x equals -3. Those are my vertical asymptotes right there. Okay, those are the vertical asymptotes. Those are the values that are not in our domain, okay? X equals a number is what type of line? X equals some number, okay? This is a vertical line. This is a vertical line, all right? So my vertical asymptotes. Now, let's try to work another one just to stress the importance of our steps for finding vertical asymptotes. Let's take f of x equals x minus 3 over x squared minus 9, okay? If I work this problem, well, this is still the same. I factor, but on top, on the numerator, I have an x minus 3, and the denominator, x minus 3 times x plus 3. Okay, simplify. What's in common here? I have an x minus 3 and an x minus 3. Those two cancel each other. And so in the numerator, I just have a 1 left. And in the denominator, I just have an x plus 3 factor left. Okay? Now, when I look at this, I set the denominator equal to 0. I have x plus 3 equals 0. That tells me x equals -3 is my vertical asymptote. So you might be asking yourself, well, what about x equal to 3, Mr. Clark? If I plug in x equal to 3, what happens? I get a 0 here, and I get a 0 here. That ends up giving me 0 over 0, which if you take calculus, you'll find out that that's called an indeterminate form. This kind of gives me the clue. If I have an indeterminate form like this, it could be the case, maybe not, but it could be the case that this is actually a hole in our graph. And for this particular rational function, it is a hole at x equal to 3. But that's different than the vertical asymptote x equal -3 here. All right, so it's important. Factor first, then simplify. and then set the denominator equal to 0, solve for x, and those are my vertical asymptotes. Okay, let's do another one. H of x equals x plus 3 over x squared plus 9. Now, once again, going through the same problem, when I set the denominator equal to 0, there was no real x where x squared plus 9 is equal to 0. So what does that tell me? There is no vertical asymptote. There's no vertical asymptote for this graph here, all right? So we don't have to worry about any jumps or discontinuities going on here. All right, cool. One example that might pop up on you and you need to be careful about, say you have some function k of x, and it's like x squared minus 4 over x minus 2. Okay, so first, what do? We factor, all right? So I get x minus 2 times x plus 2 in the numerator. Difference of squares. Square root of x squared is x. Square root of 4 is 2, right? Okay, and then, ooh, what happened? All right, let me go back. So, and then, what do we have? We have x minus 2 here. So, cancel, cancel, simplify. What do I get? I get x plus 2. As long as x is not equal to what? Well, as long as this isn't equal to 0, right? X minus 2 not equal to 0. So plus 2 plus 2, as long as x is not equal to 2. Okay? So what happens at 2? If I were to graph this, what would it look like? All right? So let's graph it. If I had some line, f of x equals x plus 2, how would I graph it? I'd put a dot at the 2 for the intercept, and then I'll look at my slope, rise 1, run 1. So it looks like it's going through just like this, okay? However, at x equal to 2, the graph is not defined. So at 2, I go up here, and there's actually a hole punched out of the graph, okay? So this k of x, it's an interesting function here. It's a rational, complicated rational function that simplifies to x plus 2 as long as x is not equal to 2. Okay, so if you were going to graph this in your calculator, all right, so parentheses x squared minus, minus 4, close parentheses, divide x, and then minus 2, close parentheses, enter. All right, when I graph it, you can see from this picture that it looks like there's some little hole. So this calculator actually more smart than your TI-84. Your 84 wouldn't show that little hole there. So that's how I will know when you're graphing your graphs if you did this just in a calculator or if you actually got it right, okay? And you knew that there was a hole at x equal to 2 there. So technically it's a line with a little hole punched out of it, okay? All right, cool.